finite-dimensional first-class constrained Hamiltonian systems and turned to the canonical description of general relativity, which of course is a starting point for any canonical quantization. I pointed out that in order to define conjugate momenta, one, of course, always has first made implicitly, often, a choice of a notion of time. And that will take on a somewhat new spirit when we come to general relativity, because there is no a priori physically distinguished notion of time. And we'll see how this plays out in the general formalism. Now, I'll just start by writing down a few expressions that were on the blackboard yesterday. So first, just recall we made a transition from four-dimensional configuration field variables G mu nu of x, the Lorentzian matrix, to a bunch of quantities that are more adapted to a hypersurface slicing. And I'm seeing here on the board that you've learned about this today in all generality. Now, we just need it for codimension 1 slicings, where I'd introduced to you kind of a three-dimensional metrics, so they are induced on spatial hypersurfaces, and then these additional data, whose geometric meaning we had also understood yesterday in terms of this splitting. This is, of course, a positive definite Riemannian metric, 3 by 3. And we had also looked at the associated velocity variables, which were given by the extrinsic curvatures. And we'd also briefly recapped their geometric interpretation, and then made a Legendre transformation. That just means expressing everything in terms of expressing the action in terms of coordinates and momenta. The coordinates were these HIJs, and they were supplemented by a bunch of canonically conjugate momenta, which are called little pi ij. So the first step here was, of course, to rewrite everything in terms of velocities. So starting from the usual Einstein-Hilbert action, just consisting of the Ricci scalar term, and then proceeding to re-express everything in terms of these new adapted phase space variables. Now, the four-dimensional integral we write also as we also decompose in a time part and a spatial part. Now the expression that then appears here is pi ij hij dot. So that's my pq dot term in terms of the fields, minus n curly h perp minus ni curly h I. Here, of course, the sum over I from 1 to 3 is understood. And the Hamiltonian is just read off from this as a function, of course, of coordinates and momenta, but also these n and ni's as a three-dimensional integral over the spatial hypersurfaces, which are called sigma d3x n h perp plus ni hi. Now, you realize I'm just giving you various algebraic expressions. I'm not presenting you the explicit algebra, although this is, tedious but straightforward. What does that mean? The first time you do it, you are struggling, trying to find all the terms and get all the indices right. So that's also a warning to you. I mean, you have to have done some of these computations at some stage to appreciate just what's going on and what are the slight technical issues involved when you do this. Now, these hi and h_perp were given as minus 2 covariant spatial derivative capital Dj pi ij of x, and the h_perp. These were all expressions that were already on the board yesterday. I'll try and make an effort and distinguish k's and kappas. So kappa squared dependent on the Newton constant. Gij kl is kind of a metric on superspace. Superspace is a space of all three-dimensional metrics. Pi ij pi kl minus square root h divided by kappa squared and a three-dimensional R. Where I had defined this curly G kind of a meta-metric, a supermetric, a metric on the space of metrics as the following expression: 1 divided by 2 square root of determinant of h, hij k hjl plus hij k hjl minus hij j hkl. This is a metric. And we had already said, well, maybe this is not, I can recognize this as vaguely as some kind of Hamiltonian. Here is my kinetic term, some linear combination with index contractions of these symmetric momentum tensors. And here is something like a potential energy. Now, what on earth these things are, well, that's at this stage a little unclear. However, now, looking at the form of the action, there's one thing you immediately realize, namely its, well, singular structure. Singular in the sense we had talked about in the context of these finite dimensional constraint systems, because, of course, you see, although we introduced canonically conjugate momenta to these ends, they were also constrained to be 0. So I haven't even included them here. That was, of course, a consequence of the fact that the time derivative of these variables never appeared in my action. Right? As a consequence, now, this is a classical expression. Of course, one thing I can do is just write down what equations of motion follow from this. When I compute now the Euler-Lagrange equations of motion, of course, what I see is, since this, with respect to the n and the ni's, derivatives do not appear, the Euler-Lagrange equations read partial derivative of L, Lagrange density, with respect to n, equal to 0. That immediately, of course, implies that whatever n multiplies into this function just has to vanish by the equations of motion. And the same holds when I vary with respect to ni. Then, of course, I immediately get an equation that these hi's have to vanish. Okay, so these n and ni's are nothing but so-called Lagrange multipliers, right? And they enforce simply the vanishing on shell of whatever is multiplied by them. Yeah, so that's our first observation. Yeah. N and ni Of course, they are, of course, arbitrary. They depend on, their fields. So they depend, of course, on the space-time points. So they enforce a couple of constraints. And the constraints are exactly three, well, there are three constraints. Hi, doesn't matter whether I write the index up or down, equal to 0. This is called the diffeomorphism constraint, sometimes also called the momentum constraint. And H perp equal to 0 is called the Hamiltonian constraint. So I mean, momentum constraint refers to the fact that, I might think of these things somehow vaguely as a four vector or something. Then I have momentum and Hamiltonian kind of energy. So this was fine. I mean, this looked like a Hamiltonian, but it's not quite a Hamiltonian. It's a Hamiltonian constraint. So it will be actually required to vanish on solutions of my theory. Okay, that's a little bit special. You think, oops, if I'm going to interpret this as an energy, why should the energy vanish? All right? Now, this turns out to be a quite generic feature and can be traced back again to the invariances of the theory, which of course caused this system to be singular in the first place. Now, of course, we've learned now in our finite dimensional analysis that we know now, if we have a bunch of constraints around, that it's important to understand what their Poisson bracket algebra is. And, for example, to test whether we are talking about a first-class constraint system, because we have already learned something about what it means for the physical degrees of freedom of the theory. And I will just quote again, that's a somewhat involved algebraic exercise to compute now the Poisson brackets of these objects. Now, this is, of course, realize it's a step up from what we did in finite dimensions, because if I now write down the Poisson brackets, they are field theoretic quantities. So the derivatives that appear are functional derivatives. So what I can already expect, if I just take the brackets of these bare expressions, are Dirac delta functions typically appearing on the right-hand side. Yes. So let me just write down what the algebra is, and then let's think a little bit more of what the meaning, what they tell us. Okay, so let us first look at the simplest case. That is the equal time Poisson brackets of two of these diffeomorphism constraints, Hi of x and Hj of x. Now, this becomes, on the right-hand side, an Hj of x, partial derivative with index I. This is y, refers to the argument y here. Yes. So, and also I should say, so these are all, this relation and the other ones I'm going to write down, they're equal time Poisson brackets. Now, this acts, the derivative acts on a three-dimensional delta function of x and y, and then there's a second term plus Hi of y del j x delta 3 of x and y. Now, we have not just delta functions, we have even derivatives of delta functions on the right-hand side. Again, this is not surprising after the remark I just made. And now here, otherwise, the right-hand side is proportional to the constraints here I started with, namely the momentum constraints. So we recognize this already as being something like a a Lie algebra relation. But let me write down the two other relations first and then discuss this a little further. What is an hi of x? Poisson brackets with an h perp of y. That gives me a right-hand side of h perp of x, del I x, three-dimensional Dirac delta of x and y. And lastly, an h perp with an h perp gives me a right-hand side, which is hij, so my metric with indices raised, curly hi, momentum constraint of x, partial derivative with respect to y on three-dimensional Dirac delta. And there's a second term, minus hij of y, hi of y, del j in direction of x, again of the three-dimensional delta function. Now this set of expressions, I mean the algebra that they generate goes by the name of Dirac algebra. If I want to get rid of these singular right-hand sides, and actually it's a procedure that is strongly recommended in actual calculation, is to smear, as one says, smear out these phase-space functions. And what I mean by this is to integrate them against kind of test functions. So, yeah, let me do it here. And it's perhaps easier if I just write these right below them. So smeared out version of this where you're using the following integrated expressions, h perp. Now, this doesn't then have an x argument, but kind of a functional dependence on a smearing function. Let me call this n, d3x, n of x, h of x. And similarly, for the momentum constraint, let me integrate this over in three dimensions over a test function which I call ni, so same symbol as the lapse and shift, hi of x. Yes, but I could use in principle other test functions, but this is of course exactly the ones that appear if I look at the integrated form of the Hamiltonian there. So they're smeared with functions which happen to have already this additional meaning, but in principle here I might just choose any other functions. I mean, so this is independently valid for what I'm going to write down now. Now, what does become of the algebra? Obviously, the right-hand sides will now be regular, right? So no more delta functions or derivatives will appear because de facto I have added two integrations. Now, what happens is that h of n I h of m j. So these are now two distinct smearing functions. Becomes an h of some new smearing function, capital K, index K, say, where this is a vector, like these were three vectors, the n and the m, so this K is also a three vector. And you obtain it by just taking the commutator of vector fields of the n and the m. And you can think of that, for example, as the Lie derivative in the direction of vector field n of the vector field m. That's an aside. Now, what are the other two relations? Smeared out momentum constraint Poisson bracket with a smeared out Hamiltonian constraint gives me back a Hamiltonian constraint with a new smearing function. And now I have to tell you how this depends on the ni and the n on the left-hand side. M is Lie derivative in the direction of vector n of the smearing function capital N, and that's the same, if you write it out in coordinates, as an ni Li n. This is, of course, just being the partial derivative. And lastly, my H perp smeared with n, Poisson bracket H perp smeared with m, gives me a H of a Ki. So this now is a momentum constraint where Ki is equal to little hij n del j m minus m del j n. Okay, now, if everyone has written this down, let me just make some remarks about what this is. Yes? This one here?
Yeah.
This one?
Yeah.
Oh, it's just another smearing function. It's just this one where I have another smearing function which I call m. Okay, so that's just keeping track that I have two different constraints. Of course, you see, you should think of these, you know, when I write down that diffeomorphism constraint, Hamiltonian constraint, of course, it's one for every space-time point x. So you really should, so we're talking about a field theory, you should think that it's really an infinite set of constraints. And in the smeared out version, the way I'm keeping track of this would be to say, well, I'm running through all possible smearing functions with appropriate, well, whatever, fall of properties to make these integrals well defined. Yes?
In the last relation, do you need to take summation over the I, which I is?
Sorry, say that again?
The index I. Do we need to take the summation in the right-hand side?
Here?
Yeah.
No, this is, look, this is an example of a diffeomorphism constraint, which depends on a vectorial smearing field like here.
So
of course, it doesn't have a free index, but I'm indicating that it depends on the vector I've put in here, and which is, however, contracted, of course, with the index on the HIs. Okay? Now, so the question, of course, what on earth is this algebra? I mean, what does it want to tell us, or maybe does not want to tell us? Okay. Now, the first relation. So these are the three-dimensional diffeomorphisms. So that are, of course, our original theory in 4 dimensions. Before we introduced this 3+1 split, had a 4-dimensional diffeomorphism invariance. Yes? Now, we've projected it in a 3+1 fashion. Of course, what one's expectation would be is that it reduces on the 3-dimensional slices just to the 3-dimensional diffeomorphisms. And that expectation is indeed correct. So this is nothing but the Lie algebra of the 3-dimensional diffeomorphism group on these hypersurfaces, capital sigma. Okay, and this is just the Lie algebra. And if I take the commutator of 2 of them, well, they relate, I mean, the arguments relate exactly as I would expect from the diffeomorphism algebra. Again, of course, the diffeomorphism group is an infinite dimensional group. And of course, its algebra is also infinite dimensional, and it's spanned by all the vectors, right, the vector fields. So we understand what this is, right? So let me give this a star. So this star is just isomorphic. It's isomorphic with the Lie algebra. Of the diffeomorphisms of these spatial hypersurfaces. Let me just call this diff of sigma, whose generators are exactly these vector fields. So also the first thing we can, looking at the other relations, is that this is a closed subalgebra of the Dirac algebra, right? Because momentum constraint with momentum constraint gives me another momentum constraint. So this closes on itself. So, and it's transparent what it means. Yes, so now, is the rest here? So it's a Lie algebra, or it's isomorphic to a known Lie algebra with a clear geometric interpretation. What can I say for the rest here? Well, unfortunately, this whole algebra taken together is not the Lie algebra of 4-dimensional diffeomorphisms. There are various ways to see that, but one way is to see that, well, it's not actually Lie algebra. And why is it not a Lie algebra? Because here in this last relation, what appears are not just the arguments n and m, but explicitly what appears are the coordinates, part of the phase space coordinates. So that is a case where, it's Lie algebra that is still fine, but it has structure functions here. And if it were structure constants, then it might have a chance of being the 4-dimensional, the relations of the 4-dimensional diffeomorphism algebra. But this is not the case. These are different relations. And in particular, they bring in a particular field dependence. Now, why are we not talking about the 4-dimensional diffeomorphism algebra? Well, because we've introduced a split, and we have introduced certain projections of the quantities we're playing around with. So this is an adapted kind of structure where, which is implicitly and explicitly depending on this slicing I've chosen. Yes. So it's not, so please keep this in mind. So the Dirac algebra is, well, it's not isomorphic, that would be the best way to say it, to diff of the original 4-dimensional manifold. Now, at the risk of again contradicting myself, of course, if it were a Lie algebra, this would have to be constant. So So it's linear, it's fine. It's linear on the right-hand side. Yes?
The x appears in curly h, and the curly h definition of curly h is that we integrate over all x. So the x dependence is gone when we have integrated it.
Yeah, no, the x dependence is here. I just wanted to indicate that it's a field. So the important thing is that this is one of the canonical variables. Yeah, you're right that the x dependence will disappear, but of course the h dependence will stay. You know, never mind whether I integrate over this function or not. So this is the statement I wanted to make. So so it's not. So what I really wanted to say, so it's not even a Lie algebra, but of course what is still the case is that it closes in the sense of the first class condition, right? Namely, that all the right-hand sides are linear combinations of the constraints. So that is satisfied. So we have a first-class constraint system, and what we can expect is that my infinite-dimensional system will be, first of all, constrained to a submanifold of phase space of codimension 4 times infinity, because we're talking about a field theory, plus these 4 constraints are also going to generate some kind of gauge transformations on my infinite dimensional phase space. So we will find exactly the same kind of geometric situation here at work we saw in finite dimensions. Okay, so here this means we have structure functions and not constants. And, well, to cut a long story already now somewhat short, if you're trying now to implement this algebra in the quantum theory, this gives you the least of problems, but the rest does. And in particular, this very specific dependence here, say on the HIJs. Okay, before getting there, let me say a couple of other things. First of all, of course, there are these constraints, but of course, there's still equations of motion I have to solve. Right? Now, there is a nice kind of a nifty little theorem that tells you the following, namely that if on every hypersurface of your theory the constraints are satisfied, I mean, as I've written them up there, so hi equal to 0 and h_perp equal to 0, then automatically also the equations of motion are satisfied. So let me just write this down. Here. So that's a theorem if for a Lorentzian space-time given in terms of M and just a 4-dimensional pseudo-Riemannian metric G mu, we have that the constraints vanish, hi equal to 0, h_perp equal to 0. On every one of the spatial hypersurfaces, sigma t, I called them yesterday, then this G mu nu, line, satisfies all 10 Einstein equations G mu nu equal to 0. I hope this is a no notation. That's the Einstein tensor consisting of R mu nu minus 1/2 G mu nu R. So in that sense, you could say, well, the dynamics is already contained in the constraints alone. And that is also the rationale one follows in the quantum theory, that at all costs one wants to, now, after one has translated, that is one possibility, these into operator equations, one then looks for kind of wave functions that lie in the kernel, in the joint kernel of these constraints. So that is one way of saying, well, these are then the dynamical relations. My quantum Einstein equations, they are not Einstein equations, but classically, of course, we have this relation, and something similar you might expect to hold in the quantum theory. Okay, let me finish here on this blackboard. Why does it always go up with me instead? Let me finish with a little degree of freedom counting. Now I have identified that I'm talking about a first-class system. Now I was starting with pairs Hij, pi, ij. Now, these constitute, well, 6 degrees of freedom in the sense of being 6 pairs of phase-space variables. I mean, 6 times infinity cube, because I'm doing that for every point x, spatial point x. I have then the constraints. So I have first-class constraints. And of those, I have 4 times infinity cube. So note here this refers again to pairs of degrees of freedom on the phase space. So before, in these finite dimensional examples, I counted these as eight directions in phase space. So, but here I'm counting pairs. So the striking twice of the first-class constraint has already been incorporated in this counting. And of course, this leaves me with 2 physical degrees of freedom. So these are my physical degrees of freedom. And, well, the counting works out. The counting of the number of what these are works out, of course, exactly like it did for the linearized gravity case. But of course, in the linearized gravity case, I had very explicitly identified what these were, in the sense of polarization states of just linear waves. Okay, but here I haven't done anything of the kind yet, but I have already established that by simply counting degrees of freedom, following the Dirac-Bergman algorithm in principle, I've reached, at least to quantifying how many of those there are in my theory. Yes?
So every constraint strikes twice.
Yes.
But we seem to have like 4 times 4 constraint equations, right?
Yes.
So shouldn't there be an 8?
Yes. Well, yes, I could have written in my own counting, this should be
12.
phase space. Yes, this
Right.
should be 12,
Okay.
and this should be 8, and then we would have 4.
Yeah. and then
phase-space degrees of freedom, but I can't.
Well,
you know, one uses these two things interchangeably, but often when one talks about degrees of freedom, one means just the kind of the configuration space degrees of freedom, or pairs of phase space degrees of freedom. So yeah, so there's really no, there's no issue here. It's just a different way of talking about the same thing. Now, once people had uncovered this algebra, of course, the question arises now, what is it? And especially, what is this H-perp doing there? Well, you can read about this in many places. Certainly, again, I would say Sundermeyer's book and references therein are a good reference. Now, geometrically, what this H-perp does, I mean, the HIs, right, they just generate diffeomorphisms in the spatial directions. I mean, so far, so transparently understood. What these H-perps do is they move these spatial hypersurfaces, well, on shell, that is, on configuration that already solve all the constraints, perpendicular to itself. So kind of create a little kind of bubble evolution, you could say. So this is the so that's why one also calls it sometimes the hypersurface deformation algebra. And if you look in Miesner, Thorne, Wheeler, I think they have so many ways of understanding this algebra. And then after, of course, the book was published, people have come up with so many other things of kind of restating and rephrasing what this is and what are the minimal conditions to derive them. And essentially, these turn out to be, well, just a shared symmetry group. So if you have really a theory that is invariant under diffeomorphisms, four-dimensional diffeomorphisms, and then you make a 3+1 split like the one we had here, you will find an algebra isomorphic to that, where then the H-perps and then the HIs, of course, will then for any given case be different functions of the dynamical degrees of freedom. This could then also include, for example, matter fields of a certain kind. It doesn't affect the overall structure of that algebra, but what each individual constraint then is as a function of fields, that will then change and depend on the theory. So this is essentially just dictated by the original symmetries of the theory, diffeomorphisms, plus my wish to squeeze it into a kind of a 3+1 kind of projected version via this preferred spatial slicings. And of course, you would say, if that is a structure you expect to recover in the quantum theory somehow, yeah, then maybe the same algebra should make an appearance, because it would then also give rise, it would induce a certain geometric interpretation of your quantum theory, which you might want to retain, or at least in some limit to retain. Okay, now I want to raise a few general issues when it comes now to the quantization of systems, which are of this first class type, or in general just have some redundancy, some gauge redundancy built in. And I want to do it by way of drawing a little, well, commutative, perhaps, diagram. So that's kind of the general issue I want to address in the remainder of today's lecture, quantizing constrained systems. Comes with a bunch of kind of questions of principle, as well as questions of practicality. Now, what is my diagram? My diagram has 4 corners. So my upper left-hand corner is the classical, now unreduced theory. That means I have here a theory. It's given to me in terms of a bunch of variables, of which I already know that part of them are gauge, and only part of them is genuine physical degrees of freedom. That's what I mean by unreduced. There is a process in principle that says, okay, let me already classically just try and get rid of this redundancy and just rephrase everything in terms of a subset of variables. And this I call then a classical reduction. So let me throw out all these superfluous, variables and arrive at some classical reduced theory. Now, this much for the classical side. Now, the issue arises, of course, I'm interested in the quantum theories. So let me, for simplicity, again, think of that as a process where I now associate with this a quantum theory. So if I do this for the unreduced theory, then, so this is my quantization procedure, whatever it is. Let me leave this open for the moment. I arrive at a quantized, unreduced theory. And similarly, if I do the same here for my classically reduced system, I arrive at a reduced quantum theory. On the other hand, of course, if I have the quantized reduced theory, unreduced theory, there's still too many degrees of freedom floating around. So somehow on the quantum side, I have also to get rid of this redundancy in some way. Let me not specify how. Let me call this a quantum mechanical reduction, whatever it is. And that should also then lead me to the bottom right-hand corner. And of course, this is what I'm looking for, right? This is what I'm interested in. Quantum theory of my genuine physical degrees of freedom. And certainly one question that immediately poses itself is that a commutative diagram, right? Do I get to the same theory if I go this way, right? This way, or that way? So are these two things equivalent? Should they commute as a matter of principle, or what? Well, to start with, well, I mean, any statement or many statements that people will make about this issue will already make some assumptions about, what these arrows mean. Now, my general statement would be that a priori, it doesn't seem to me given that as a matter of principle, these two procedures should lead to the same result. Now, what I mean by this is, if I'm quantizing this system, I'm clearly talking about a system with more degrees of freedom that I'm quantizing and that potentially, of course, interact with my physical degrees of freedom. That's not the case here. Here they're just not there. Right? So, for example, and of course, potentially these other, maybe, I don't really know what they do in the quantum theory. Do these other degrees of freedom kind of entirely decouple? In very simple cases, I can write down they may seem to do this, but in general, who knows, right? They could have, I mean, the extra degrees of freedom I'm quantizing here might just have some kind of influence on my final quantum theory, even if then I impose some reduction here. So it seems to me that as a matter of principle, it's not clear that this should be commutative. Now, if you make more specifications about what these arrows mean, and well, then it might, in the end, well be commutative. Who knows? Now, practically, there are great limitations on what you're actually able to say about this question in concrete situations. Because, of course, unfortunately, for generic classical theories, we simply have no idea what this arrow is. We have more of an idea here if my original space was a vector space, when I have a Fock space quantization. Okay, these are cases that I typically can handle, and if this is kind of sufficiently simple. After having reduced, very often I just have absolutely no clue what this arrow is. Right. In addition, there is certainly, in the same sense as, well, quantizations by themselves are not kind of unique one-to-one arrows, the way you implement a quantum mechanical reduction for surely is also not unique in general. What do you mean by that? So you see there are various pieces of this diagram are simply not very well defined. And for the case of gravitational theories, if you include this to mean, general theories which look similar, which are diffeomorphism invariant, maybe live not just in 4, but in other dimensions, we are very limited. I mean, we can hardly do anything to get to here. And in 4 dimensions, actually, well, we haven't really got to here in a way that people agree on. So these are just a few remarks to keep in mind. Now, this is even more unpractical usually because of the involved nature of physical phase spaces, reduced phase spaces. So the more practical way is usually this kind of this red arrow. And what one then does is going this red arrow. This means this quantum reduction process is usually taken to be something one calls the Dirac quantization. So let me just write this down. So that's at least a popular way of implementing this reduction. What does this consist in? I still have 5 minutes to give you a sketch. More about this tomorrow. First, one quantizes. That's a prescription. Quantizes. It's a kind of the redundant, I call it. I mean, gauge in the sense of gauge, presence of gauge degrees of freedom. The redundant, unreduced theory on some Hilbert space H. We're talking about canonical quantization, of course. So one pretends that this is just a physical theory and applies to it, whatever quantization, standard quantization procedure is at hand. One then kind of implements the constraints on states. On states. And let me revert to my notation of constraints as classically as phi A, what we had yesterday. Then you'd say here, I'm projecting out states, a subspace of states from a Hilbert space, which satisfy a certain condition. So that will then give rise to a kind of a physical Hilbert space. Namely, if they are in the kernel, or as one also says, are annihilated by each one of the quantized versions of these classical phase space functions. So that determines, hopefully, a sensible subspace of my Hilbert space for me, for all constraints A. Yes?
The second is like Because when we quantize, we can't implement such conditions, so we have to relax it a bit.
Well, this usually works quite fine. I mean, in quantum mechanics, I'll talk about this next time. I mean, we had yesterday, we had kind of a condition that was P3 equal to 0 classically. Just to give you an example of what happens. Right? Now, that was my classical constraint. Now, how would this be translated to the quantum theory? It would say phi hat, in this case, is equal to pi 3 hat, simple Schrödinger quantization, and my condition on wave functions would then be P3 hat on psi that depends on, say, variables Q1, Q2, Q3, something like this, is equal to 0. And this is, of course, proportional to d by d Q3, this operator. And then it would just tell you, well, the physical wave functions are those which are constant or do not depend on Q3. And then, of course, I have to see how I handle this within the set. These are not then a priori square integrable because, well, they could just be constant as a function of this third direction. So, and they have, but it's pretty straightforward what this means. I mean, I just will drop then this coordinate essentially from the physical as an argument of for my physical wave functions. So this is how this is to be understood. But clearly, yes, especially in field theory, additional consistency issues will arise. And sometimes this is too strong a condition, indeed. So certainly one consistency condition, I'll just mention briefly now. So recalling, of course, that what we had classically was phi A, Poisson bracket with phi B equal to FABC phi C. We must have that at the operator level, phi hat A and phi hat B imposed on wave functions also vanish. And unfortunately, well, why is that not immediately guaranteed? Of course, in general, I'll have to say something about what these constraints are. But a simple reason could be that, for example, if these here themselves depended, were functions and not constants, then, of course, they would also have to be quantized. So in a way, then these right-hand sides would become some, F hat ABC phi C. But when they're quantized, of course, an issue of operator ordering comes up. So it might just be that when I do the computation of this commutator bracket, even if it's, well, reasonably, well, if it's almost preserved, it might come out as something where the phi C happens to come out, say, on the left-hand side of these, on the right-hand, the F's on the right, to the right of these quantized phi hats. And if I imposed this condition then, right, if I impose this on my wave functions, of course, it's not covered by the fact that, these annihilate them. But I would tend to get additional new conditions from where, these functions annihilate the wave functions. Which means, unfortunately, that in general, I will be killing degrees of freedom which are already physical. I mean, I'm over-constraining my system, certainly compared naively to what happens classically. So we can already see that many new issues will arise when I try to now translate what I did classically for these constrained systems to the quantum theory. And we'll meet more of these things later. I mean, there are, of course, very simple examples where everything kind of decouples, kind of the gauge degrees of freedom from the physical ones, for instance, like here, where this goes through without problems. But of course, these are just very simple finite dimensional toy examples, and they're usually, the real case we are interested in physically is much more difficult. Yes?
So a question, if you wanted to go the other way.
This way here.
Yeah, so
yeah.
Say we, say example of 3D, if we fix gauge before,
yes.
Before we quantize,
yes.
will we not get something that's physically different than the QED that we don't fix? Will it be okay?
Well, no, I mean, if I gauge fix consistently, of course, the final result ought not to depend on it. Of course, what also tends to happen, you see, of course, and what would has to happen when you do the same in QED, you'll have to destroy other nice aspects of the theory, like explicit Lorentz invariance, or sometimes even something like locality. That doesn't necessarily mean everything is completely going wrong or even wrong at all, but it just, other nice kind of manifest properties of your theory might get lost. Of course, you can still then get the correct, physical answers. But it's just not as obvious, and it makes it more difficult to calculate. And nasty things like non-local expressions popping up. This is kind of one of the troubles you then meet in the explicit calculations, and which may discourage you from going this way. Again, like electromagnetism is still a reasonably simple theory, but when it then comes to gravitational theories, this is not. Yeah, this is so nonlinear that it's not very promising. You can't really do very much. Okay, see you tomorrow.